In this video, I'm going to do this problem. It's a brake system with pivoted shoes. So you see here we have a drum, has diameter of 13.5, and then those pivoted shoes, you see here there's a pivot here, there's a pivot here. Then we're going to see do this problem. So let's see first the statement. It says the shoes on the brake depicted in this figure covers 90 degree subtend a 90 degree arc on the drum of this external pivoted shoe brake. It's rotating counterclockwise. The actuating force P is applied to the lever, you see here, and then the rotation is counterclockwise, as I said, and then the coefficient of friction is 0.3. What should be the dimensions E in order to eliminate friction moments on each shoe? Alright, so then that says part B is find reaction forces, do FPD diagram of lever handles, brake levers, this one and this one, and then find reaction forces and find everything in terms of P. So this P is like input force, and find everything. Does the direction of the rotation of the drum affect the braking torque? So that's the question we're going to answer at the end. Alright, so before doing this, let's look at the lecture related to this. We looked at this, your book looks at this. So we have if you have a brake with symmetrical pivoted shoe here, as you see, let's see what variables, important variables we have here. This is like the arm, through this pivot, it's free to rotate about it. So the forces on that pivot acting on this is Rx and Ry, you see those. Alright, and then what? The distance of the pivot from the center of the drum, we call it A, okay, and then in this picture you see the rotation of the drum is counterclockwise. So the friction force that we have applied to this pad or the shoe, you see FDN is going like down here like this because of the rotation. So if you see the that friction force, if you take integral of that, the net force is going to go down, so that will be cancelled by Ry. So Ry is there to cancel that net force caused by friction downward acting on the lever. The normal force that we have, dN, you see if you take integral of that because of symmetry, if it is symmetric, those guys, they are not going to have any y component, dN, if you take integral of that, but it's going to have a x component, right? So we did in your book does it, and we did in class. We showed you the model, mathematical model here. So what we found was this: the moment caused by the friction force on the lever will be this equation, mf. You see this equation here. In order to have this moment be 0, so why we want to have friction moment be 0 on this lever? The reason is we want this lever to be moment free. Otherwise this arm is not gonna stay like symmetric. So if geometrical variable, like most important one is this A, if it is A is picked right based on this equation, if you set this this moment equation, if you set this parenthesis, the bracket equal to 0, you will find magnitude of A such that we'll have this parenthesis 0, and in other words the moment friction moment will be 0. So if A is equal to this, so what are the variables here? R is the radius of the drum, theta 2 is the angle of the shoe. So let's look at this guy. Theta 2 is this angle, theta 1 is the lower angle. Theta 1 and theta 2, if they are equal, let's say they are equal, then FA is equal to this, 4 times radius sine of theta 2 divided by sine of 2 times theta 2 plus 2 theta 2. Then that will be symmetric. I mean the moment, friction moment will be 0. So this thing is not going to spin or rotate, right? It's going to stay like vertical, no rotation. That's what we want. Alright, so that's part A of this problem is actually asking for that. It says what should be the dimension of E? Look at the E. E is actually, we have two of these shoes, so if I want to relate E to A, that derivation we had in book or in class, E here, let's see if I can make this guy working. Let's see, change my alright, so E that we are trying to find is basically 2 times of the A, right, in that statement, I mean in that derivation. So yeah, so part A says find the E in order to eliminate frictional moment on each shoe. So in each shoe the moment we want that be 0, so find the E. Alright, so that's one part. Part B then says find do FBD of these arms, and then what, and then find the forces, right? Forces at this each pivot, here, here, and here. And then part C says does the directional rotation of the arm affect the braking torque? So we have two of these guys, two shoes. Right now we are assuming the drum is going counterclockwise. So what happens if it goes clockwise? Does the brake torque is going to change or not? Alright, so this is the problem statement. So let's look at the lecture again. And alright, so I talked about this. The reaction forces Rx and Ry, how they are related to our geometry and our loads. Let's see that equation. The derivation in class we had it. Rx is gonna get simplified to this. Rx equals PA BR divided by 2 times of theta 2 plus sine of 2 theta 2. PA is the maximum pressure between the shoes and the drum. That's gonna happen at theta equal to 0 at this point, right? So knowing that PA, we can find Rx. So B is the width or depth, R is the radius of the drum, theta 2, those are angles. Ry is going to be equal to this equation. Okay, and then what? So these are two equations. And then what else? The problem statement was asking about braking torque. So the braking torque integral, we have to evaluate this integral. So see, TB equals the brake force that goes on the drum is F times dN. If you multiply it by R, it's going to give me the torque, braking torque on the drum. So FdN times R, we have to evaluate that from theta 1 to theta 2. Alright, so that's the braking torque. Then again, if theta 1 and theta 2 are equal, we have symmetric shoes. And then that simplifies to this guy. 2 times of PA R squared FB sine of theta 2. Again, P is maximum pressure. R is the radius of the drum, F is coefficient of friction, B is the width of the shoes or the depth, theta 2 is the angle. Alright, if your if your brake is designed in a way that A equals to this, in other words, there is no friction moment, then this equation simplifies to this. After some algebraic operations, TB is going to be A times F, coefficient of friction. A is the distance. Okay, let's go up. Let me show you A again. Distance of the pivot from the center of the drum is A. Will be A times F times Rx. Rx is like actuating force. You can think of it that way, in X direction. Ry then is going to be F times Rx. F times Rx. Yeah, so you can think of this Rx and Ry to be your actuating forces. Right? So if I have my A picked in a way that there is no frictional moment on the arm, then you guys saw that the actuating force Rx and Ry are going to be related to torque like this. So braking torque on the drum, AF Rx. Ry is going to be related to Rx equal like this, F times Rx. So we're going to need these later. Okay, so let's look at the problem now. Part A was, I talked about it a little bit. So if E is going to be equal to 2A, and then if A is picked in this way, that's equal to this, I'm now going to need the equation. You have 4 times R sine of theta 2 divided by sine of 2 theta 2 plus 2 theta 2. Right, if A is picked like this, then your system, your shoes are not going to be rotating, no moment on those. So part A is easy. We just replace these and substitute them in this formula. So R is the radius of the drum is 13.5 divided by 2, so it will be about 6.75 inches. Theta 2, so let me show it to you. This is theta 1, this is theta 2. So theta 2 is equal to theta 1. They are 45 degrees. But when you use this formula, we got to make sure that those are in radians. So A equals 4 times of radius 6.75 inches times sine of pi over 4, like theta 2, divided by, again, sine of 2 times of pi over 4 of pi over 2 plus 2 times of pi divided by 4. Okay, let's find this. Right, so we have a calculator here handy. 4 times 6.75 times sine of 45. Right, so 45. Let me find the sine. Okay, this is the denominator. Let me see. Yeah, this is the denominator. Let me write it down. 19.09. Is that right? And then I have sine of pi over 2, which is 1, plus 2 times of pi divided by 4. Okay, so we have 2.57. All 7. Yeah, okay, so let me invert this guy. Multiply it by 19.09. Okay, 7.42 7.42 inches, and E is basically 2 times of this guy times 2, so 14.85. 14.85 inches is the E I need in order to have those moments, you know, no frictional moment, right? So this means that with this choice, these shoes are not going to be tilting, you know, it's going to stay vertical. Alright, so that's a good choice. Alright, so we found the E, part A, but let's look at part B. For part B, we need to do FVD of that lever, that L-shaped lever first. So we see I have it there like this, L-shaped thing. Let's, by the way, name these guys. So if I call this A, this point A, B, C, then what? Let's call this D, E. So at this point I have this B here, P, I'm sorry, and then here I have, let me erase this. So if I, okay, so this is like a, there's a 2 force member here. This is FAB, if I call it. And then at this here pivot, I have, if I call this force CX and CY. So let's find these forces first. Okay, so this length is 6 and 3/8. And I have this height is like 3 inches. You're gonna find everything in terms of P. Alright, so then, by the way, let's look at this. This AB, this entire length, I found it be 14.85. This height is 3. I'm gonna need this angle here. So let's find that angle. It's gonna be arctangent of, okay, 3 divided by 14.85, arctangent of that guy. Oh, sorry, I made a mistake. Okay, 3 divided by 14.85, and then arctangent of that. So arctangent of that, 11.4. This angle is 11.4. Alright, so if I want to show it here, this angle, 11.4. Okay, so let's write the equation of equilibrium. So first, let's see, takes moment about C. Summation of moment about C must be 0. This P is doing clockwise, negative P times 6 plus 3/8. Okay, then I have this FAB. FAB, okay, is doing clockwise too. So plus, is it doing clockwise? No, it's doing counterclockwise. So plus FAB times, the arm is 3. I need to know the angle between the force and this vertical line, which is gonna be, okay, and then I have to multiply sine of that angle, which is 90 minus 11.4 equals 0. So from here, FAB equals, let's do that. I will take let me see, take this to the other side. 6 plus 3, 8 divided by 3 times sine of 90 minus 11, 6 is going to be 78.6. Alright, so let's find FAB. This, by the way, is going to be in terms of P. I have P here too. So let's find it. 6 plus 3, 8 divided by 3. Divided by 3. And then divided by 70x.6 sine. Alright, so 2.17. 2.17 times of the P is FAB. Alright, then summation of forces in X must be 0. So C, this one, I called them wrongly. Okay, so this one is CY. This. Okay, CX is going to the right, FAB is going to the left, negative FAB. Cosine of 11.4 should be equal to 0. CX equals, let's see, FAB 2.17 times 11.4 cosine. There you go, 2.13. CX is 2.13p, and then CY. Okay, so for CY, I have to say summation of forces in Y must be 0. So P is going down, CY is going up, FAB is going down, so negative FAB sine of 11.4 must be 0. So CY equals, P goes to the other side, FAB 2.17 times P times sine of 11.4. Alright, 11.6, no, 11.4, I'm sorry. Okay, so let's calculate this. 2.17 times 11.4 sine. Okay, is this plus 1.43. Okay, so CY is 1.43p. There you go. CX is 2.13, and then FAB is this. Alright, so now CXCY, now we look at this arm that the right shoe is sitting on it, and let's look at the FPD of that guy. Alright, so force, that what I had there, by the way, these forces, we look at the bracket, now I'm looking at the arm. So look at the direction of CX and CY. I chose them right. So now we have to invert them here because I'm looking at this action reaction. So you know what? I'm gonna have here 2.13p. CY was 1.43. Should go down 1.43. 1.43. Okay, at this bottom I'm gonna have dx, I'm gonna call it dx, and dy. Dy. Okay, at this pivot here, the shoe sits. Let's look at that's gonna depend, the forces on that, it's gonna depend on the direction of the rotation of the drum. So you see, if the drum rotates like this, the friction force, you see, it's gonna drag this shoe down. So I'm gonna call this guy Ry. Ry is gonna be like this. See this? And then at the same time also this is gonna push this pivot to the right. You see it's in contact on the left side. It's gonna push it to the right. So if I call this Rx is gonna Rx, Ry. We need to find these. The problem is asking for those. By the way, this arm entire length is what? 1528. From here, this pivot to the bottom is 7.78. Alright, so we need to use equilibrium and we need to solve this, right? Okay, we have one body. How many forces? 1, 2, 3, 4 forces. I have 3 equations. So I need one extra equation from the friction study or the brake study. So let's go back here. Here's the key equation here. If A is picked properly with according to this equation, then you remember I said that the shoe is not going to spin. This shoe is not going to spin or rotate at all. It's going to stay vertical. Then we had that equation. You guys saw that. That's going to be a key equation. Ry equals F times Rx. So Ry is going to be, F by the way was 0.3 times of Rx. So this is the extra equation I need. I have 3 equations of equilibrium and I have this one. So this should give me all these forces, right? So Rx, Ry, dx and dy. So let's do it now. Summation of moment about point D must be 0. So 2.13 going counterclockwise. What is the arm? Alright, and then who else? Rx is going clockwise. Nobody else is making moment, right? So Rx times 7.7x, and then from here Rx equals okay, let's do it. 2.13 times 15.28 divided by 7.78. Okay, Rx is 4.18 times of the P. Okay, everything was in terms of P. Then Ry will be like this guy times 0.3. So 1.25. 1.25 of the P. Alright, so we found Rx and Ry. By the way, we had this equation. Braking torque is gonna be A times F times Rx. So if I want to write that too, so braking torque on the right side, A F Rx. Right, let me double check. Yeah, alright, so A is half of E, 7.42. Coefficient of friction 0.3, Rx is 4.18. So see guys, we have the braking torque on the right side, 7.42 times 0.3 times 418. There you go, 9.3 times of P. Alright, so, but the problem was asking for forces, other forces too, so dx and dy. So how do I find those guys? Summation of forces in x direction must be 0. So dx is going to the right, Rx is going to the right. Who else? 2.13 is going to the left. Yeah, that's it, right? So equals 0. So dx will be equal to, yeah, to calculate this. 4.18 minus 2.13. So I found dx equal to, okay, you know what, these two is gonna go other side, become negative. So negative 2.05 the p. Then summation of forces in y must be 0. So dy is going up, ry is going down. That was the other force, 1.43 is going down. So dy equals, is it, okay, you know what, I want to use my calculator. So this guy in terms of P2, so 1.25 plus 1.43, 2.68, 2.68 of the P. There you go. If we found those pivot points at this here, right? So we found everything, right? The Rx, Ry here. So the right arm and the brake is studied. So let's look at the left one now. Alright, so let's look at the left one. Let's see, where can I find a spot? Maybe this is a good spot. Let me do it here. Let's do this arm here. So we have here, let's call this guy EX, we call this one EY, FAB. Okay, FAB is like this. How much was FAB, by the way? FAB was 2.17 times of the P. So 2.17 times of the P, we need to convert, break it into two components like this too. This angle is 11.4 degrees. Okay, and then at this point let's figure out the direction of Rx and Ry. So the left shoe and the right shoe are similar, but the only difference is, look, this guy's rotating like this, so it's gonna actually drag this up here like that. So if I wanna call Ry is gonna go like this. You see on the other side was going down, but here is gonna go up, and then the force, the Rx one, is gonna be like this. Alright, so yeah, so this is what you need. Okay, so this horizontal force is going to 217 times cosine of 11.4. 2.17 times 11.4 cosine. So 2.13. This guy is 2.13 P. Okay, this guy, let's find that guy. It's gonna be 2.17 times 11.4, but this time sine. So sine of, I made mistake. Let's see, 11.4 sine times 2.17. Okay, 0.43. Okay, so how about Rx, Ry? By the way, those guys, right and left, they are the same thing, the angles are the same, coefficient of friction is the same, geometry is the same. So you know what, Rx and Ry, they're going to be the same. So Rx, let me write it down. The only thing is the direction, right? So 4.18 P, Ry equals 1.25 P. so there you go. Then we can find Ex and Ey. So summation of forces just let me see. They must be the same. R, no, just hold on. Make sure I didn't make mistake. Okay, so Ry is 0.3 times of Rx, and then yeah, okay. We can write this relationship that Rx is still is gonna be equal to what? Yeah, I want to make sure that I'm not making mistake. You know, Ry is gonna be 0.3 times of R. Yeah, I gotta, you know, what I said is not right. All I can say is this, that since the left side, again, A is picked in a way that this doesn't spin, all I can say is that Ry equals 0.3 times Rx. So again, from equilibrium, we have to find the new Rx. So that was my mistake. You know, the Rx, which is like the actuating force, is not going to be, not necessarily they are the same. But we have this relationship between R1 and Rx, and that one is because of the shape, the geometry, and the fact that A is picked based on this equation. Alright, so yeah, so I take that back. So summation of, let's see what we get. We still need to use the equilibrium equation. First one, the most useful, summation of moment about point E must be 0. So 2.13 times, this one is clockwise, this entire arm length, which is 15.28. This is clockwise. And then we have Rx going counterclockwise. How much is that arm? 7.78. Alright, so equals 0. So let's see how much Rx we are gonna get this time. Alright, so 2.13 times 15.28. So right? Yes. Okay. So 2.13, 15. Divided by 7.78. Yeah, Rx, let's see how much it comes out. 4.18. Yeah, so it turned out they are the same. But I couldn't have claimed that at the beginning. Okay, so came out the same. Alright, so and then Ry, 0.3 times of this, 1.25. So you guys see the difference between left and right. Now is this, that the direction of forces is different. Alright, so now let's look at the pivot forces. Summation of forces in x direction must be 0. So Ex is going to the right, 2.13 is going to the right, Rx is going to the left. So Ex, Rx, this one is going to the right, equals 0. So Ex equals 2. Let's see, 4.18 minus 2.13, 2.05. Okay, 2.05 times of the P. Summation of forces in Y must be 0. So Ey is going up, Ry is going up, 1.25 of the P. And then who else? 1.43 P is going up too. So Ey comes out negative 1.9. No. Sorry, 1.68 P. That one is different. And my direction was wrong. so it's gonna go, it's not gonna go up, it's gonna go down. Yeah, it's gonna go down. It has to drag it down. The reason is because of this guy, you know, this friction force is gonna drag this up, so this pivot should drag it down. Alright, so we found reaction forces everywhere, right? So which pivot is experiencing larger load in overall? Looks like, yeah, the right one. The right one, the net force here is bigger than this one. Alright, so last part, it was saying draw the free body diagram of this. Okay, does the directional rotation of the drum affects the braking torque? Okay, so the braking torque, look, by the way, let me find the braking torque for the right side, for the left side, I'm sorry. Again, it's gonna have this AFRX. Since RX is the same, it's gonna be 9.32. So you know what? The left side, the braking torque on the left side is gonna be 93 times of the P2. The unit, by the way, whatever the unit for forces, pound if it is pound, for example, and then inch. For example, if force is pound, then it's gonna be pound inch. So the left and right we must add to each other, so it will be like 2 times of 9.3. So let's go to that question. If the directional rotation changes, let's see our equation. So you see, if the direction changes, if you look at the left, what happens if the direction changes? Let me see what happens. What is going to change? I'm going to now, let's see, if this spins clockwise, this was, like at first it was saying it was rotating what direction? I forgot. Direction of rotation of the drum is counterclockwise. Okay. Did I assume it? Okay, I assumed clockwise. Yeah, alright, so that's okay. So I assumed it was going clockwise, right? And I did my solution based on that. Let me see, yes. So clockwise, yeah, this is going to go down, this is, okay, and therefore this one is going to go up. Okay. You know what? I solved the problem based on clockwise, but what happens if it is counterclockwise? So if that happens, let's see what changes. The problem is not going to change actually. So the only direction of forces. So if it goes counterclockwise like this, let's see. For this one, this was the FBD here, right? So let's see what happens. So the force Rx is going to be the same. So let me show it with red. Ry is going to go up instead this time, right? But relationship between Ry and Rx is the same thing. Then look, then what happens? Relationship between the magnitude is the same. So then taking moment about point D, by the way, that's not gonna change the Rx, right? Rx is gonna be the same. Ry is gonna be the same, but you see right now, it's gonna go up. And then, so the torque, by the way, the torque is not going to change because it's just function of Rx. So the torque doesn't change, alright, for this one. And the forces, the only thing is, let me see what else it may change. Rx and Ry, the only thing, the magnitude is the same, the direction Ry changed. So let's look at here. So summation of forces in Fx Okay, then dx is not gonna change because only ry changed. And then if you do summation of forces in Fy, so this time ry was going down, now it's gonna go up, so it's gonna be like this. So this will be like positive, and then yeah, so dy is gonna change if the rotation is counterclockwise. The dy is gonna be 1.43 minus 1.25. Yeah, 0.18. So this is what I'm gonna get. dy will be 0.18, right? So upward still, 0.18 times of the p upward. So that's what happens, but brake wise TB doesn't change. So let's look at this guy. If again is counterclockwise, let's see what forces happen. So ry here, instead of going up, is gonna go down. It's gonna be my new ry, but again look, so I'm taking moment about E, right? Rx is gonna come out the same, so Rx is gonna be the same. Ry is gonna be 0.3 times of this guy, but this time is gonna go down. And then when you are doing the force analysis for summation of force in the x direction, Ex is not gonna change because Rx is the same. But okay, here look, the Ry 1.25 now is going negative. Yeah, so what happens here? Ey goes other side, 1.25 becomes positive. 1.25 minus 0.43 times of the p, so 0.82 times. So what I'm getting, the p, right? Yeah, so I actually kind of did the problem both ways, you know, what happens to the reaction forces, you know, if you rotate counterclockwise or clockwise. I did both of them, right? But what is important for the last part, says, does the direction of rotation of drum affect the braking torque? The answer for that is no. You guys saw that. Because that was because Rx didn't change, right? Rx didn't change, and then since the friction torque is only function of Rx, the torque doesn't change. So that's the answer for that. Okay, I hope you guys find this useful.